So, what we're going to do here is chapter 9, and we are right here. Oops. Okay. Oh, wow. Okay. Come on. It work better if I do that? Yes, you're going to work better when I do that. Okay. Let me come back in. All right, so last time we left off, we were talking about strong acids, strong bases, and how they fully dissociate in solution. Now, antacids are what you use to neutralize the excess stomach acid in your stomach. In your stomach, you have what's called stomach acid. That's the HCl. Whenever you have like something you've eaten and it's disturbing your stomach, and you start going, and you get that like burning sensation, that's actually what's called acid reflux, right? And what's happening is you have too much stomach acid, or the stomach acid is being disturbed, or you've inflamed your stomach in some way, and it's causing that acid to come up into the outside of the stomach, typically in the lower part of your esophagus, which attaches to your stomach, okay? And that's going to further inflame the situation and cause it to be even worse, okay? Now, there's several ways you can deal with that. One way would be to take like Pepcid. Let's see, I had that in here somewhere, I think. And that's going to be blocking the potassium hydrogen pump that's in the lining of your stomach. Another way you can deal with that is you can take antacids. So antacids are going to be a base that is going to neutralize some of that acid, okay? And so there's actually a variety of antacids, but they all have the same thing in common. They're all going to be a base that when you put it in the acidic environment of your stomach, it's going to partially neutralize some of that acid in your stomach, okay? Now, they're typically not very soluble weak bases, so that OH minus is not damaging. If you were to drink a strong base, by the way, this happens quite often, in case you're wondering. You'll hear about like a lawsuit about this somewhere in the nation pretty much every year, okay? Because sodium hydroxide, lye, looks almost exactly like sugar. And so people keep lye at like food stores where they're making like barbecue, or they have a lot of like ovens and stuff, and it's the oven cleaner. And so they use that to scrub the ovens, right? And then somebody leaves it out, and then somebody really stupid puts it into the water, the tea, and then instead of sugar you have lye, sodium hydroxide tea. And it just destroys the person's esophagus. They're incredibly fortunate if they survive it. Okay? Very, very dangerous because it actually turns you into soap. So if you were to drink a strong base, it would actually turn you into soap on its way down. Okay? And it would, of course, damage the stomach if it was in there. And so you want a very weak base that's not very soluble. And so this is going to be a weak electrolyte, a weak base. Okay? Because if you have too much OH minus concentration, you're going to actually turn your stomach into soap. You'll destroy it. So aluminum hydroxide, very common for this use. Magnesium hydroxide, again, very common for this use. I think magnesium hydroxide is more popular in the ones that I typically take. I haven't actually taken an aluminum hydroxide one in quite a while. But yeah, I just don't see them very often. Maybe there's other brands that use aluminum hydroxide more. I guess maybe I just use the same brands every time. Might be. Now, the aluminum hydroxide actually is going to produce constipation. It also binds the phosphate in the intestinal tract. And so this actually can cause weakness and loss of appetite, which is why I think that companies have mostly been moving away from this. But ones that specifically are trying to get you to not have diarrhea anymore sometimes could use this. Okay? This would be a very effective way of both stopping the acid reflux and giving you, constipating you, making it less diarrhea, right? Magnesium hydroxide actually has a laxative effect. And so if you take the magnesium hydroxide ones, like melcomagnesia is used for a laxative effect, magnesium causes a laxative effect. And so you are going to end up running stuff out you the other end at an increased rate. Okay? Now, these side effects are going to be less likely when you use the combination, because you get both a constipation effect and a laxative effect. And so they are, in many cases, in antacids combined together to try to modulate those effects. Okay? Now, this right here is actually the reaction of the magnesium hydroxide with the HCl. And so it actually reacts the HCl in your stomach. It does an acid-base neutralization reaction. And it's going to give you the magnesium that is aqueous, dissolved in your stomach acid and your liquids. And it's going to give you water. Okay? Okay. This right here is calcium carbonates. Now, calcium carbonates are very commonly used to neutralize acids because they also react with acids. They are basic themselves. But they actually do a reaction where they produce CO2. So this would be calcium carbonate. This would be similar to like baking soda is calcium bicarbonate. Your teeth is calcium carbonate. So this would be your teeth whenever you have acid around them. This is like carbonic rocks, like limestone and stuff. This is also those tablets, like menthols. When you put them in Coca-Cola and acid, they foam up a bunch, right? Because they're releasing CO2. Okay? And so you've actually seen a variety of these before. You may not have realized it. Okay? Chalk also is a carbonate as well. Remember when we made the chalk, we were talking about calcium carbonates? Okay. And so you put that in with an acid, HCl. What's going to happen is it's going to produce calcium chloride, which is aqueous, water, and CO2, which is a gas. They're not super popular as a treatment for stomach acid, because what are they going to do? They're going to make CO2, which is a gas, right? It's going to bloat your stomach, isn't it? And then you'll end up burping a lot, farting a lot, and having a lot of issues like that. You'll feel very, very full, okay? Bloated, quite unpleasant. People used to take just straight up baking soda and swallow it for their stomach acid problems, by the way. You can do that. It works. It doesn't really cause any huge problems. I wouldn't recommend it. You'll feel bloated and it'll be quite unpleasant. But So when calcium carbonate's used, about 10% of the calcium is actually absorbed into the bloodstream. It will elevate the levels of serum calcium, serum being the liquids around your bloodstream. The calcium carbonate is not recommended for people who have peptic ulcers or a tendency to form kidney stones. Kidney stones, again, being a calcium precipitated out. And so increasing the amount of calcium if you form kidney stones is not necessarily a great idea. Okay? Because you're more likely to form more kidney stones. Also, peptic ulcers. Does anybody know what a peptic ulcer is? Everybody know what an ulcer is? Yeah, that's like those little wounds on your mouth, right? Okay. So those are ulcers that can happen on the stomach lining. If you have a wound on the stomach lining and then you bloat the bladder, which is the stomach, it can cause that wound to worsen, right? It'd be like if you had a wound on your lip and then you decide to stretch your lip out a bunch. It's probably not a great idea, right? Now, sodium bicarbonate, this can affect the acidity level of the blood. It actually elevates the sodium levels in the bodily fluids. It's also not recommended for treatment of peptic ulcers. So if you have a peptic ulcer, again, you'd produce carbon dioxide, and again, that is not a great thing to do. On top of that, it does elevate the sodium level of your blood. So sodium bicarbonate would be like baking soda. Okay, this is some different examples of these antacids. I don't take any of these, but right here is the Alka-Seltzer that you've probably played with when you were a kid. You may have like thrown into Coca-Cola bottles It made them go boom. Okay. You can do that. You can also do that with this right here, which is like the Pepto-Bismol. It doesn't work as well, but anyways, anybody have any questions?
What is the first one?
This one right here,
Yeah, no.
Anfogel. You probably never have gotten it or used it. These ones would be more used for constipating people. If you have like diarrhea that's uncontrollable and you are in danger of dehydrating from it. Yeah. And so it's unlikely any of you would use that. If you have, then you've had an experience like that where you've had diarrhea that's uncontrollable and they needed to actually stop it. Normally they just have you drink more water. Yeah. This one right here would be stool loosener. So it'll give you, it'll unconstipate you. Yeah. And then this one right here would be balanced. So it's used to reduce the amount of acidity of your stomach. And it tries to hold a balance where it doesn't really constipate or loosen your stool. Yeah. This one mostly you would see it in like hospitals and stuff. But you could get a script from a doctor. Yeah. Not commonly seen. People don't usually use it. At least I've never seen people use it. I know of people that have had it given to them, but I've actually never had somebody in my life have to use it. So now, some chemical reactions will, after forming product, reverse and reform your reactants. These are referred to as reversible reactions. And so again, these are reactants over here. On the left side is always reactants. Here we have an equilibrium arrow. It goes both ways in this reaction. And right over here we have products. And so what this reaction is telling you is this reaction goes both ways dynamically, right? And what's equal at the equilibrium is the rates of the reaction are equal in both directions. So you're going to have no overall change in this equilibrium reaction, okay? So once you form the ammonia over here, it's going to reverse and it's going to reform the nitrogen. You'll get a continuous cycle of the molecules in the reaction, going back and forth. But the overall state of the reaction isn't going to change. Remember that example with like nightclub or a theme park? So the same number of people are coming in as going out, right? And so your overall state of the theme park stays the same. Same number of people overall, right? Okay. Now again, that's called chemical equilibrium. When it's a chemical reaction that does this, you use this equilibrium arrow to indicate that. And again, it's showing you that the forward and reverse reactions are both happening, and they're both happening at the same rate. Okay? Remember, it's the same rate. It does not necessarily mean you have more products than reactants, or you have equal amounts, or whatever. Okay? It just means the rate's the same. Right? For example, if we were to go to an incredibly popular nightclub, right, it would be far less people inside than are outside, right? No. It would be the same number of people inside at all times because it would continuously fill up as people leave, right? But, so it's an equilibrium state. But your numbers of people inside and outside, not equal at all, right? Yeah, not even remotely, okay? If we go to a really unpopular nightclub, we might have the reverse state, don't we? Almost everybody's inside, nobody's outside, right? Yeah. And let's say they're still at carrying capacity, somebody goes out, somebody comes back in, we're still at equilibrium, aren't we? Yeah. But again, we have far less outside than inside, right? So, okay, so equilibriums have constants. Notice that I kept saying they don't change, right? They're going to stay the same. And so they're going to have an equilibrium constant. So if we measure those concentrations of the ammonia, nitrogen, hydrogen that are present in that formation of that ammonia reaction, we can actually do a calculation, which is the equilibrium expression, which is this right here, and calculate the equilibrium constant, which is that large K. Okay? So again, that's the equilibrium constant right here, which is the large K. The expression is just the calculation for it. That's the formula, right? The formula is actually super easy. It is the concentration, these brackets mean concentration, of your products to the power of their coefficients divided by the concentration reactants to the power of their coefficients, okay? So I want you to kind of memorize this in two parts. We have the equilibrium constant. An equilibrium constant is products over reactants, okay? So concentration products over concentration reactants. All right, everybody got that with me? Okay, say it with me now. Equilibrium constant, products over reactants. Okay? If you say it, you'll actually remember it better, by the way. So you're doing yourself a real disservice if you don't say it with me. Okay? Now, again, these are going to be the molar concentration. That's that molarity that we've been talking about, right? Moles over liters. Okay? Now, if there's more than one reactant or product in this formula, then we're going to get something that looks like this. So this is going to be a balanced chemical reaction or balanced chemical equation. These coefficients are those numbers that are before each of the species. So for example, if we looked up at this one over here, that would be the 1 here, right? And that would be the 3 here. Okay? And then the coefficient would be 2 for that one. Right. So this is again an equilibrium arrow here. This is going to be K, the equilibrium constant, equals the concentration of the product to the power of its coefficient times the concentration of the next product to the power of its coefficient, and this divided by the concentration reactant to the power of its coefficient times the concentration reactant to the power of its coefficient. So, the concentration of your solids and liquids, that are pure solids and liquids, they do not appear in these, okay? So, for example, these right here are gases. They would all appear in this, okay? Aqueous would appear in this. If you have a pure solid, it says S, that's not going to show up, okay? If you have a pure liquid, like water, in that previous acid-base reaction, it's not going to show up as well, right? And the reason for that is pure liquids and solids are going to go to 1, which is called unity, okay? And so if you take the power of anything of 1, what do you get? 1 to the 100th, 1 to the 10th. You just get 1. Yeah, 1 times 1 times 1 times 1 is 1. It doesn't matter. And so if you have a pure solid or liquid, it's just going to show up as 1 in this. Doesn't do anything. You can just completely ignore it, okay? All right, now, if we have these values of K, these equilibrium constants, if K equals 1, then that's going to have about an equal amount of products and reactants. So K equals 1 tells us that the amount of reactants and the amount of products is going to be about equal. Okay? Now, if we have a K that's greater than 1, then what we're going to see is that products are going to be the predominant. So for above 1, we're going to produce more products. That's our very unpopular nightclub, more products, right, than reactants. Okay. If we have a K less than 1, then what you're going to see is reactants predominate. And so that's going to be that bottom term is larger, right? If we have K greater than 1, then that top term needs to be larger. See that? Which is products. So, K greater than 1, products. You have more products than reactants. K less than 1, then more reactants than products. K equal 1, same amount. Okay? All right, now let's talk about how chemical equilibriums shift. You can actually shift chemical equilibriums by adding one of the reactants or changing the heat of the reaction. And so, for example, Le Chatelier's principle, if you apply stress to an equilibrium, this is going to cause the rate of the forward or reverse reaction to change. This will help to offset that stress and regain that equilibrium. And so let's look at this reaction right here. If I were to add nitrogen, I'm going to put stress on this, and this is going to cause this to shift right. Okay? So if I increase my nitrogen levels, it's going to shift over right to the products. If I increase my amount of reactants, it's going to shift towards products. Okay? Okay, what if I take away a reactant instead? Well, it's going to cause it to shift towards reactants. If anybody has a water bottle that's closed next to them, you can actually play with it, and it becomes a really, really easy demonstration to do. So, if we increase the amount of nitrogen, the reactant, it's going to look like a little slide, isn't it? And all your water would shift towards the products, wouldn't it? Okay? And that's because equilibriums shift towards products. All right? If you remove reactants, well, it's going to look like a little slide, and everything is going to shift towards reactants, isn't it? Okay? Same thing happens if you manipulate products. So if I was to add more products, it's going to shift towards my reactants. If I take away products, it's going to shift towards products. And I'm going to produce more of them. Okay? Okay. Now, the effects of temperature on equilibrium. Well, this is going to depend on whether this is exothermic or endothermic. Okay? And so in this reaction we were looking at right here, this was actually what's called the Haber cycle. And it's a production of nitrogen. You use it a lot of times to make fertilizer. Okay? So this is a very common industrial reaction to make fertilizer. Right? Which is responsible for feeding about 2/3 of the people on the planet. In case you're wondering. This is why we had the big population boom. Now, if we take this reaction, we can add, if it's an exothermic reaction, well, we can just put heat as a product. Because heat is produced, right? And therefore, if we cool this reaction, what happens to your products? Shifts towards products, doesn't it? If we heat this reaction, on the other hand, what happens? Shifts towards reactants. Okay? So typically when this Haber reaction is done in industry, they're big vats, and they actually cool these. Okay? If they let these get too hot, they're going to stop producing the ammonia right here that they're trying to produce for the fertilizer. Okay? So again, if you heat this, it's actually going to shift towards the opposite direction, right? If you cool this, it's going to shift towards the heat. It's going to produce more heat. Okay. Okay, so if it's an endothermic reaction, this is going to be the opposite shifts. Heat would be on the reactant side. And so it's going to always shift away if you increase, shift towards it if you decrease. Okay? It's the same pattern for all those. Now, this right here is just a summary of all those patterns that I just talked about, in case you forgot what I said. Okay. So, again, this is the principles of equilibrium we just talked about. We're going to apply them to acids and bases now. And so remember that when you look at weak acids and weak bases, they're equilibriums as well, aren't they? And so here we have a weak acid, that's vinegar. Okay? Acetic acid. Notice it reacted with a pure liquid, didn't it? Which is water. Okay? It gave us the conjugate base here and the hydronium ion right there. These are all aqueous. Okay? Okay, so if we were to do the equilibrium expression for this, this would be K equals concentration of product, so that right there, concentration reactant, that's right here, concentration of the other product, right here, concentration of the reactant, right there, and that's going to give us the equilibrium expression. Note, there is something really nice about acid-base reactions. Because the definition is you donate A, meaning 1 proton, you accept A, meaning 1 proton, they're always 1-to-1 ratios. Yeah. And so the powers here are always 1. So that actually makes it kind of nice whenever you're looking at acid-base equilibriums. Their powers are always 1. So you don't have to worry about that as much. Now, did anybody notice the reactants down here? We're missing that, aren't we? What happened?
This is solid.
Yeah, we got pure liquid, right? Yeah, pure liquid or solid. goes to 1. We don't need to list it. You're exactly right. So again, water, pure liquid, don't need to list it, right? Okay, so these are actually some different Kas. That's what actually the K is referred to as for an acid. Okay, it is the K equilibrium constant for an acid. It's called an acid dissociation constant, right? So it's just the equilibrium constant for an acid. When you look at it, it's for the acid dissociating, isn't it? And that's the name for it. Acid dissociation constant. I know, chemists have no imagination. Now, this right here is the different names for these different acids. Right here we have the formulas. Notice that there's some actually kind of interesting ones here. This right here is one of the forms of phosphate in your blood. This right here is water, actually. Water can act both as an acid and a base. Its Ka is 10 to the negative 14. That's actually where the pH scale that goes from 0 to 14 comes from. That maximum 14 is that right there. Okay. Anyways, here's some different ones. Hydrofluoric acid, if you ever watched Breaking Bad, that's the one they dissolve the bathtub in the body. Trying to dissolve the body. Accidentally dissolve the bathtub. That would kind of do that. I don't know if that amount would fully dissolve a bathtub like that. I have a funny feeling it would actually get used up mostly in the process and wouldn't go very far. But as far as they would want it to go. But it would definitely dissolve through and fall down through the other floor. And it'd be incredibly dangerous. They would have probably died from it. Yeah. A drop of hydrofluoric acid landing on you, you actually have to go to the hospital immediately. You'll die not from the acid itself, but what happens is the fluoride strips the calcium from your bones, and it is so painful you'll die from the shock from the pain. Yeah. And so to fix it, they actually band off your arm and pump a bunch of buffer into it and swell it up to about 3 times its size. And that's how they treat that. But if you don't go in fast enough, you'll likely die from it. Yeah. Very, very brutal one. Used to use hydrofluoric acid all the time because that's the only way you can remove silicates from glass. You literally just take off a layer of the glass. Yeah. So, for weak acids, the value of Ka is less than 1. This can indicate that the more acetic acid molecules that are present at the equilibrium than the acetate ions. So what we're seeing is the Ka is less than 1. See all these Ks that are less than 1 here? It's going to favor this side of the reaction, right? The reactants, not the products. And it greatly favors the reactants. So most of your acetic acid is actually going to stay together as acetic acid. Only a fairly small amount is going to dissociate to form the acetate ion. Okay? All right. Now, because all weak acids can attain equilibrium in solution, they all have Ka values at a given temperature. If you were to change this temperature, the Ka value is going to change. Okay? And so these equilibrium constants, they're constant for a given temperature, not for all temperatures. Each weak acid is going to dissociate to a different extent. So your Ka values are different from acid to acid. That's why we had this table here. We have the different acids. They have different Ka values. Okay. The larger the Ka value, the stronger the acid, and the more protons that will dissociate. So you saw here that water is not usually considered an acid because it's an incredibly weak acid, right? If we look up here, we see ones that are stronger, like acetic acid. This is a stronger acid than water, right? And that's why we normally call it an acid. Still a weak acid, but it's better acid than water. Okay? Quite a bit better of an acid than water. This would be an example, phosphoric acid right here. This is a stronger acid than vinegar, right? Acetic acid. Still a weak acid, though. Still mostly stays together, mostly does not dissociate. Okay? Strong acids would have Kas that are up in the 10 to the 12ths, positive 10 to the 12. they would be 10 to the 14ths, that sort of thing. Okay? So 10 to the positive 14. That would be something like a strong acid. And those would essentially completely dissociate in solution. That's what makes them strong acids. Now, this right here is carboxylic acid. That's the carboxylic acid as in like amino acids. Remember that amino acid, the acid part? That's the acid part. This is going to dissociate to give you carboxylate. Again, those carboxylic acid groups on the amino acids typically are going to favor this side in most cases. However, on an amino acid, you actually have an amine as well, don't you? So amino acids are kind of fun. They have a base, that's a weak base, and a weak acid on the same molecule. Yeah, and that's where the amino comes from. So it has the amine here. Amines can be protonated, and so this would be the acidic form of the amine right there. Okay, and that's a protonated amine right here. Okay. Or an ammonium salt. That's another way of referring to those. In amino acids, typically you would refer to that as a protonated amine. Okay. Now, let's consider this dissociation of acetic acid. We have CH3COOH. Right here we have, again, the acetic acid. It's going to react with the base, which is water. That acetic acid is going to lose its proton, lose its H+. It's going to go to the conjugate base, which is this form right here. And notice that's lost an H, it's lost a plus, hasn't it? Okay, the water over here is going to be acting as a base. It's going to gain that H+ and go to the conjugate acid. And so notice, on both sides of this reaction, we have an acid reacting with a base, and then on the other side, we have the conjugate base reacting with the conjugate acid. Okay? Because one side gained a proton, the water gained a proton, right? It now has an extra proton. So over here, it can actually act as an acid over here, doesn't it? And remember, this is an equilibrium. It's going to continuously go back and forth. Okay? Okay. Is everybody okay with that? Did anybody get lost? Again, we're losing that proton to the base. It then becomes a conjugate acid because now it has an extra proton, doesn't it? So, kind of like if you borrowed $5, you then have $5 you could loan someone, can't you? Okay, now, conjugate acids and bases. So the CH3COO-, this is the conjugate base of the acetic acid. Again, it is a base now because it's a reversible reaction. It can take on an H+. It had one before, and it can take one on again. Okay. The conjugate base is going to be the CH3COO-. The conjugate acid, on the other hand, is going to be the H3O+. Remember that it once had, it did not have a proton before. It has gained a proton now, and so it can lose that proton and go back to water. Okay, and so that is now the conjugate acid. So remember, you always have conjugate acid-base pairs. They're always related by that presence of the H+. If it's the acid, it's going to have an additional H+, right? If it's the base, it has lost an H+. Okay? All right, now weak acids are generally considered to be in the form of HA. You can actually just write them out as HA. Literally, you have the H from the H+, right? And then you have A to stand for acid or anion. It actually stands for either or both. This right here would then be the conjugate base of that acid, that weak acid. And so that's going to be A-. Remember, it lost a hydrogen, so it lost the H, right? And it lost a positive charge, so it's a negative charge now. Okay? And so that is the conjugate base of that weak acid. That's just a very generic way of representing this, so you don't have to write out the specific acid-base pair every time you do a problem. Okay? Okay, so this right here is an example of a base. We're going to react with water again, and water in this case is going to act as our acid. Okay, so we have the amine here reacting with water. The amine is going to take on an H plus because that's our base, right? That will form our conjugate acid. Water, on the other hand, is going to lose an H plus. It's going to go to OH minus, and that will be our conjugate base then. Okay. Everybody see your acid-base pairs? Notice again, sounds like I've said 8 things, but realistically I've only just said one thing over and over, haven't I? Okay. We lose an H plus. We go to the conjugate base, right? Losing an H plus is the acid going to the conjugate base. Gaining an H plus is the base going to the conjugate acid. Okay, now, what are some of the rules for writing these out? So conjugates will always appear on the product side of your chemical equilibrium. They're always going to be products. That's why they're called the conjugate. They're conjoined to the reaction. Okay? Conjoined to the reactants. So when the proton is donated from the acid, the conjugate base form will have one more negative charge than the acid from which it formed. So if we started with a positive charge, we're going to end up with a neutral charge, right? If we start with a neutral charge, we're going to end up with a negative charge. If we started with a 1 negative charge, we would end up with a 2 negative charge. We always just shift down our charge by a -1. Okay? When a proton is accepted by a base, on the other hand, it's going to always gain a hydrogen and a positive charge. And so you're always going to go to a more positive charge. If we started with a base with a 3 minus charge, a -3 charge, what charge would we end at the end, the product?
-4.
For the base.
Oh, for the base of -2.
Exactly, yeah. Yeah, we're going to add a positive charge, -2, exactly. Now, our total charge of reactants is going to equal the total charge of the products. Whatever charge you had for reactants overall has to be the same for the products, because that's counting up your number of protons and electrons, isn't it? You can never change those numbers, so your overall charge, both sides, has to be the same. Okay, now, again, this is just the summary of all these concepts, but we're applying it to a biological setting, aren't we? In fact, in this case, we're going to apply it to oxygen transportation. So the binding and release of oxygen through the body is going to be partially controlled by a weak acid-base equilibria. This right here is your acid-base equilibria that's going to partially control that. Okay, and so your protein, which is hemoglobin right here, this is what actually transports the oxygen in your blood cells. This is going to carry your oxygen from the lungs to the tissues through your bloodstream. Okay, and so that's that one right there. Both protons and oxygen are going to bind hemoglobin, but they do so with the opposite affinity. So if you bind protons to your hemoglobin, what's going to happen is your oxygen is going to release. If you bind oxygen, on the other hand, you're going to release your protons. Okay? And so the concentrations of your acid and oxygen change. You're going to actually change your equilibrium. So again, this is your equilibrium of oxygen on the hemoglobin right there. This one's the hemoglobin without the oxygen bonded. Okay? And so let's say we're at your lungs. You don't have a lot of acid buildup at your lungs. No lactic acid buildup. That would really hurt. Thank goodness we don't have that. And what are we going to see? Well, we're going to see this form, right? The oxygen's going to bind to the hemoglobin a lot. Okay? Okay. So now we go out. We go to the tissues. We have lactic acid buildup because we're exercising. We're running from that tiger again. Okay? So what's going to happen when our hemoglobin gets around a bunch of acid? Well, this is the acid right here, right? If we increase this concentration, it's going to shift towards this direction, isn't it? And so our O2 releases, a bunch of O2 releases in the area. That's really good because we're running from that tiger. We need more O2 in our muscles, right? We're going to keep running from the tiger now. Thank goodness. We hopefully don't get eaten that day. Okay? Okay, what if we look at the other way? So we have low oxygen levels at our tissue, right? That's going to cause our oxygen level to be lower, isn't it? Okay? And so what direction does this shift? Well, more hemoglobin releases oxygen, doesn't it? Yeah. And so low oxygen levels cause hemoglobin to release more oxygen in the area. That would be our muscles using up all that oxygen again, isn't it? Okay? So again, we got away from the tiger. Woo! All right. Now, we're breathing real heavy. We're getting lots of oxygen in our lungs. What are we doing here? So oxygen levels are going to be very high, aren't they? We've added lots of oxygen to our lungs. And so this is going to shift this equilibrium towards the bound hemoglobin. So our hemoglobin is going to start binding more and more oxygen, isn't it? And that's going to get our hemoglobin fully bound. It's going to go out to our tissues where it's low oxygen levels, and it's then going to release a bunch of oxygen because those are low oxygen levels there, right? Going this way. Can everybody see that hemoglobin's actually just running through this cycle? This equilibrium shifts every time you do a circuit from your lungs to your tissues. Okay. All right, now let's talk about the autoionization of water. Excuse me. So when we're talking about water, water can both act as an acid and base, and you may have been going, but Dr. Clausen, if it acts as both an acid and base, won't it react with itself? And if you thought that, you are absolutely correct. Okay? Water is both an acid and base, and so water does react with itself, actually, which is pretty funky to think about, right? Water's sitting there reacting with itself all the time. What's happening is that water actually establishes an equilibrium itself, okay? And that's the water acts as an acid, the water acts as a base, it'll produce the conjugate base and the conjugate acid right here. The conjugate base of water is OH minus, the conjugate acid of water is H3O plus, okay? And so whenever you're looking at a water solution, you actually have constant levels of OH minus and H3O plus in that water, okay? Okay, this equilibrium right here has an equilibrium expression, but it's kind of interesting one because notice one side is all pure liquids, isn't it? So you completely drop one side. Okay. So this is called Kw. It's the autoionization of water, the equilibrium constant for the autoionization of water, Kw again. And again, it only has the products here for the concentrations because the reactants are all pure liquids, or the water. Okay? And so that's the Kw right here. Now, how does this relate to the pH scale? Why in the world there's 0 to 14 pH scale, right? Well, that's because 0 to 14 pH scale is assuming you're doing everything in water, okay? So, when you see pH 7, what you're actually seeing is that the H plus concentration equals the OH minus concentration, and that's at 25 degrees Celsius, okay? So, at 25 degrees Celsius, both of these values would be 10 to the negative 7, and that would give you 10 to the negative 14, which is that K value for water, right? The Kw for water. Okay. That's what's referred to as neutral because your H plus and OH minus concentrations are equal. Okay. That does mean that the neutrality point, that pH 7, being neutral, does change when you heat and cool water. Not by a lot, but by a little. Okay. So, if the acid is added to water, it's going to increase the H plus concentration. It'll decrease the OH minus concentration. This is going to cause that solution to become acidic, and that's what we refer to as acidic. That means it's going to have a pH that's below 7. Okay, that's because we're going to increase the H plus concentration. If a base is added, that's going to be more OH minus concentration than H plus concentration. So your OH minus concentration increases, H plus concentration decreases, and that's referred to as a basic solution. Okay. Now, I will note that most aqueous solutions are not neutral and will have unequal concentrations of H plus and OH minus. The majority of solutions you deal with in everyday life will not be neutral. Neutral solutions are actually fairly rare. Okay. Your sodas, the water you drink, you may see like alkaline water. That's basic water. Yeah. So very, very rare to actually have a neutral solution that you experience in life. Okay, this again is an acidic solution. It's going to have a concentration of OH minus that is less than 10 to the negative 7, concentration of H plus that is greater than 10 to the negative 7. Okay, neutral, they're both going to be 10 to the negative 7 at 25 degrees Celsius. And when we're talking about basic solution, your concentration of H plus is going to be less, so it's going to be less than 10 to the negative 7. Concentration of OH minus is greater. Okay. Now, again, that concentration of the H plus, that's actually what defines the acidity or basicity of a solution. Okay? And those concentrations, they're going to typically range in water from 1 molarity to 10 to the negative 14 molarity. Right? This is pretty close to a 0 right here. This is a very small concentration. Okay? This number right here is a pretty big concentration for H plus in solution, right? It can get a little bit higher than that, but you will probably never see a solution that gets higher than that, okay? It's pretty unusual. Now, notice how big the difference in these numbers is. That's incredibly inconvenient to think about. Yeah, I mean, these are 10 to the 14 is like a billion times a billion, right? And then plus and times another 100. So it's a very, very small number. Okay? This number, on the other hand, is just massive compared to that other one. And so to represent that huge range, we have to take a log of that range. Okay? If we take a log of that range, that's going to range from 0, right, to a 14 number, isn't it? Okay? And so what pH is it's the negative log of the H plus concentration. So you just take the log of the H plus concentration and flip its sign. Okay? And that's all pH ever was. So every time you heard pH, it was just the negative log of the concentration. Okay? Negative log of the H plus concentration. P literally means to take the negative log of something. So anytime you see a P in front of something, that meant they took the negative log of it. Okay? You'll actually see this if you really pay attention to the news and stuff, and they actually put the tables and stuff from the scientific reports. You'll see it for things like vaccine binding constants. You'll see it for things like the pollution in a river or lake. This is the sort of concentration level of lead. You'll see this for things like acidity, of course. But you'll also see it for things like they'll sometimes see POH numbers. That's the negative log of the OH minus concentration. You can see it in terms of if you ever look at a pollution of a river and you're talking about the oxidation of things in it and how the fish are dying, you'll see a PE. And that's the oxidation numbers. Okay? Reduction numbers, actually, but yeah. Now, again, that's negative log of the H plus for pH. Okay, so let's look at some different pHs and how they relate. Now, living things prefer a constant pH. They need a pretty tight range of pHs, though this pH level does change depending on where you're looking within that living thing. For example, our stomach is acidic. It has a very low pH. Our intestines are basic. It has a high pH of 7. And if you were to start looking in our mitochondria, they're actually quite acidic in some parts of them. Okay? So those pH levels do change depending on the environment. Okay? Now, notice the pH scale goes from 14. It actually goes down to a -1 is the lowest. You don't normally see that. So typically you're going to see something more on the level of a 0 would be the typical what you'd see in life. But if you get concentrated HCl, that's very, very concentrated, it'll actually fume off the HCl, so be careful if you ever see it. You'll breathe a little bit of if you're not careful. What you'll see is that pH will actually go to a -1. Okay. Battery acid, on the other hand, would be like a 0 if you were to use one of those acid batteries, those old style ones, not the lithium ones. Okay. This is lemon juice up here. It's a little bit above pH 1, somewhere between pH 1 and 2. Soft drinks, vinegar, those would be pH 2 to 3-ish. Beer is typically like pH 3-ish. That's what gives it its kind of sourish taste. Okay. Tomatoes, pH 4-ish. Urine, coffee have about the same pH actually. A little disturbing thought. Which is pH 4 to 5. This is milk and rainwater right here. Milk is just slightly acidic. And it does have a very, very, very mild sour taste, but it's almost not, right? Very close to being neutral. So pH 6-ish. Saliva is about the same pH, and so you don't normally taste the sourness of milk unless you've accidentally eaten something basic recently. Pure water would be around pH 7. It's almost never actually pH 7 though, because you have other stuff in it. Now, this right here would be your blood. It's typically a little basic. You have here seawater. This would be baking soda when we're dissolving baking soda. Soap, ammonia right here, like ammonia Windex cleaner. That's actually what makes it a really effective household cleaner, is because it's quite basic. This would be hair remover and oven cleaner up here. Oven cleaner being very, very basic, actually. Okay. Now, you can only get up to 14, a little over 14 actually, and around -1 in water. Okay. If you're curious, you can actually go beyond those limits as long as you're not in water anymore. Okay. What's blocking those limits and causing those limits is the fact that you have more water than anything else. And so whenever you put anything else into water, you're actually affecting the equilibrium of water. Okay? That's actually what you're playing with. So all of these things are all reacting with water, and you don't have any of these left. You just have the water, it reacted with water. Okay? So all the stuff that would have reacted with water, reacted with water. And then you just have the stuff that isn't going to react with water because that's your equilibrium. Yeah. Okay. Now, again, normal blood is actually around pH 7.35 to 7.45. Anybody ever heard of acidosis? No? Not at all? Okay. So acidosis is when your blood actually goes below pH 7.35. Your blood starts becoming more acidic than it should be, and you'll have a lot of trouble breathing, actually. And so that's actually why when people have trouble breathing because they're like having panic attacks, they have them breathe into a bag because they start developing acidosis and they can't get oxygen where they need it, and they need to regulate their breathing. Okay. Okay, anyways, there's a variety of other reasons you can have acidosis, by the way. Your blood starts becoming more acidic than it should be. Okay. pH paper is going to be embedded with dyes that are called indicators. These dyes are pH sensitive, and so when you put them in environments which are more acidic or basic, they'll actually change color. Anybody read anything that we're doing this next few weeks? So this week I'm showing you how to sample, right? And I'm giving you pH paper that has and dyes that are embedded so you can see color matching to the pH. Okay? You're going to then go out and sample and get 10 samples. Next week we have colloquium. You should go to the colloquium on Tuesday. You won't have any lab otherwise. Not from me at least. And there's a quiz that's available that you need to fill out 2 of those presentations that you go to. Okay? Okay. Now again, on Thursday and Friday, don't have to show up for lab, okay? With me. Okay. That's next week colloquium. You'll see there's a quiz on there. There's not an in-person lab. Okay. This Thursday, this Friday, or Tuesday if you have the Tuesday lab, you would have shown up for lab and we would have done the sampling. Okay? Okay, then the week after that colloquium, so next week is colloquium, the week after that, we're going to have one where you're just going to report those pH paper measurements from your sampling. Okay? And so you'll use the pH, take pHs of 10 different samples that you take around you. Okay? Okay. For example, the drinks you drink are really great ones to try out. Sometimes it really catches you by surprise how acidic or basic something is that you normally drink. Usually acidic. Okay? Okay. Now, you're going to calculate pHs. Whenever you calculate pHs in your homeworks and exams, if we're given a 0.05 molarity HCl solution, it's going to be very easy to calculate your pH. So your HCl is going to fully dissociate because it is one of the 7 strong acids that you're supposed to remember. Okay? And so all you need to do is the HCl is equal to the concentration of the H3O plus. This is then going to be the pH equals the negative log of that concentration. So all you need to do is you just go, well, pH equals negative log of that 0.05. So you type 0.05 in your calculator, you hit log, and then you flip that sign. Okay? Now, can everybody see LOG here? Okay, you need to use the base 10 log. That's what that's called. LOG. There is another type of log on your calculator, which is called LN. Okay? That's the base E log. That is not the same thing. Do not use LN. Okay? If you use LN, you will get wrong answers every time. Right? Really do practice with your actual calculator you're going to use on exams. Okay? Because one of the leading reasons people get these questions wrong is they just never do them on their calculator. They get on the exam, they have no idea how to use the log function of their calculator. And it becomes a disaster. Okay? Okay, so if you take the negative log of this value, what you see here is that log is base 10. What that is the number of 10 times that you're looking at. So this number right here is 1.3 10 divided by. So it's divided by 1.3 tens to get that. See how it has one decimal place down? Like that's a 1/10, right? And then this would be another 10th. So it's a value that's above 1/10. It's not quite 2/10, which would be another 0 here. That's where that number's coming from. Okay, that's how logs work. In case you're wondering. All right, now let's talk about calculating the H plus concentration from a pH. Well, to undo that, we can do it a couple of different ways. Some calculators have an inverse log function. That button is actually the same thing as this right here, which is 10 to the x. Okay? So you'll see one of those buttons on your calculator. And what that is you're taking whatever number you have in there, and you're putting 10 to that power. Okay? So to go from a pH to the concentration of H+, you take 10 to the negative pH. So take 10 to the power of the negative pH. And that will give you your H+ concentration. So if we have a pH of 2, this would be 10 to the negative 2. Okay? 3.5, it would be 10 to the negative 3.5. Okay. Our pKa, or acid strengths, are going to be compared by comparing Ka values typically. You often use pKa's instead, which is the negative log of the K's. We still have 4 minutes, folks. The values closer to 1 are going to indicate a stronger acid. Remember, P is the negative log number of that Ka. So it's, again, negative log of Ka when we talk about a pKa. Very commonly used on tables because they're much smaller, much easier to write numbers. Okay. Again, it's going to be seen just like the pH scale. Very easy to compare these whole numbers instead of numbers that are in scientific notations. If we make a comparison for those acid strengths, we're going to compare using the pKa values. We'll have a range that typically ranges from 0 to about 60. The smaller the pKa, the stronger the acid. So the closer that number is to 0, the stronger your acid will be. Okay? All right, now, this is some different examples with your pKa's here and your Ka's here. Okay? See how they're just negative logs of these values right here? Okay. And so, for example, if we look here, we see that this pK is 2. Over here, we see this pK is 12, right? This one right here is the stronger acid. Okay. This over here is by far and away the weaker acid. In fact, this is typically called a base, okay, because it's an incredibly weak acid. All right. This right here would be a slightly weaker acid than this one. How do I know that? Because this one has a lower pK. Okay. Now, we look over here. Again, these are the pKs of some of the acids and bases we've seen. And so this right here is your carboxylic acid. It has a pK of 4.76. That would be the Ka right there. This right here is going to be that protonated amine, or ammonium ion right there. That's going to have a Ka of 10 to the negative 10 here. We take the negative log, we get 9.20, which is the pKa. Okay. Okay, so what's the relationship between the pH and pKa? Well, if we compare the pH and the pKa for weak acid solutions, we can tell whether the weak acid or its conjugate base form is going to be present in higher amounts in that solution. So when we discussed pharmaceuticals, we noted those molecules contain charges, that they're more readily soluble in the aqueous solutions, which means that they can dissolve in your bloodstream better. When they're on charge, they can pass through the hydrophobic barrier of your cell membranes, right? And so depending on your environment, you can have more molecules that are charged, more molecules that are uncharged, okay? So if we compare this propanol medication used for high blood pressure, the acidic form is going to be charged, the basic form will be uncharged. This right here is the acidic form, this is the basic form, okay? And so what we see here is if we have a pH that is less than its pKa, your H plus concentration level is going to be higher, and this is going to shift you towards the charged form. Okay? If we have the opposite, this is going to shift us back towards this deprotonated form, which is the neutral form. So that's if the pH is greater than the pKa. We're going to actually have most of it in the neutral form. Okay? So when we get into the stomach, it's going to all protonate, go in the bloodstream. When we get away from the stomach and the pH starts lowering, it's going to deprotonate, and you're going to have it start going in your cell membranes. Okay? And so that's how drugs deliver. All right, I'll start on this next time. You all have a wonderful day. Have a fun Halloween. Have a wonderful weekend.